Welcome to day 20 of the macOS and iOS Security Internals Advent Calendar. Today we will looking into GXF, the guarded exception levels, and the PPL layer in XNew. What are guarded exception levels? Basically, guarded exception levels are an extension from Apple to the ARM64 CPUs. It's proprietary. And the idea is that instead of putting security relevant code into EL3 where it's guarded from the rest of the system, Apple has invented their own exception levels that do something similar basically. The community calls these exception levels GLX. Not sure what Apple calls them internally. Because there is, as far as I know, no official documentation of these. The code running in GLX is basically more privileged than code running in ELX. So when Apple did this, they introduced a number of new system registers at EL1 to be able to configure GXF. These are GXF config EL1, GXF status EL1, GXF enter EL1, and GXF abort EL1. All these names are basically taken from Asahi Linux, who, as far as I know, have named them because there is no actual documentation, as I said, of these names. So the next thing that Apple created were two new custom opcodes to basically enter and access this GL level. And the first one called gEnter, and you can see the binary code on the slide. When we see this opcode, it means that the CPU enters the GL1 exception level, and execution then basically continues at whatever address was configured into GXF enter EL1. To leave these GL1 exception level, the CPU needs to run the gexit opcode. You can also see the binary representation of that down below. This opcode will leave GL1 and execution will then continue at ELR_GL1. So it's basically the exception link register for the GL1 exception level. Again, all these names coming from Asahi Linux, and they are likely not exactly what Apple is using internally. So now when we are in GL1, we also have access to new system registers. And here you can see the most important of these system registers. We have TPIDR GL1, we have VBAR GL1, SPSR GL1, SPSR GL1, ESR GL1, ELR GL1, and FAR GL1. Again, the system register names are derived from Asahi Linux, but basically they make sense because they are the same register names as you would see in EL1. So now this new GFX mode is basically used for the PPL layer that is in XNew. First of all, most of this PPL layer in XNew is basically closed source, so Apple does not give out the source code. They only publish basically with the KDK and so on a binary blob of the code for GL1. Yeah, we're trying to go through this here and understand what this actually does. So the idea is that basically all the really security sensitive code in XNew is now put into the PPL. And the idea here is that even when you have a memory corruption in the kernel, and you can manipulate the memory in the kernel, you will not be able to reach certain areas because they are locked away in this GL1 code. So yeah, the PPL code is basically executed in this GL1. And the way this works is that when you have a PPL function like here, pmap find PA PPL, what it will do is it will take the handler code, which is in this case 12, it write it to x15, and then jump to this gxf ppl enter function, which will take care of entering gfx mode and executing the handler. The code will then continue to execute gxf ppl enter, and when you look at the code, you will see that there's some initial checks up here, but down here is the binary representation of the genter opcode. Once this genter opcode is executed, the CPU will switch to GL1 and will execute whatever is in gxf underscore enter underscore EL1, which in our case is gxf ppl entry handler. So this handler will then be executed in the new exception level. So this new code will now run in GL1. And when you look at what this code is doing, you will see again there's a number of checks going on here. And in the end, it will execute the ppl trampoline start, which is then responsible for starting the dispatching of the actual handler. So when we look into this ppl trampoline start, we will see that this function is quite long. And it looks up the ppl handler via the ppl handler table and the x15 handler number. So as you can see, this is basically just a direct lookup of this handler from the table. And the actual execution of the handler will then be given to ppl dispatch. And ppl dispatch will basically make use of the handler table lookup. But here, let's see what the table is. We can see here the table is defined like this. We have each of the possible handlers here. There's currently 60 hex entries in this table, and 9 of them are basically null, which means 9 of the handlers are, let's call them deprecated and unimplemented. Yeah, but in our case, this here was the pmap find pa internal, the 12 that was executed from the outside, and this would be the one that will be executed by our code. So let's continue to actually look into the dispatch code. So the ppl dispatch basically will do nothing else than actually call the handler, which is in x10 at this point. And as you can see here, this is using x9 as the context for a pack branch. So this handler table is actually protected with pack. So once this code finishes the handler, it will continue here, and eventually when you pass the ppl dispatch, you will finally see that it executes the ppl return to kernel code. So because at some point we need to exit GL1 and go back to the exception level 1. And when you look at this, what's going on here, you will see that actually the first thing that happens is that the exception link register for GL1 is written with ppl exit. And then when the gexit opcode is executed down here, the execution will actually continue and ppl exit in EL1. And because this is now code that runs in the kernel again, it's not considered secure, secret anymore by Apple. So this code here is actually part of the official XGNU source code. So you can find it in OSFMK ARM64 lowcore.s. But this code here eventually will actually just return to the caller of the API function. So, and that's basically it, what I wanted to show you today. So this is how PPL is basically implemented, and this is how Apple can ensure that certain code gadgets must be called from the kernel via the gxf enter, because otherwise this code will not actually work correctly, and also it will basically not have access to the memory that needs to be manipulated in order for certain security features to be switched on or switched off or worked around. like for example, certain read-only memory. So yeah, this is it for today. Let's meet tomorrow for the next door in the Advent calendar.